So what we've got here is a little experiment to think about radiation, or at least emitted radiation waves. So inside here, I don't know if you can see, this is very much a homemade experiment. We're out of the lab, we're at home. So I'm using a candle as my heat source. But inside here is one of my temperature probes. All I did was take a piece of origami paper, 4 centimeters by 8 centimeters, fold it in half. So it's a 4 by 4 centimeter square. Inside I taped it's actually a thermostat, but it works as a surface temperature probe here. It's going to connect by this cable to my little data logger over here. And so that's actually tracking the temperature of these two I've got stuck on the wall at the back. One that, instead of being in white paper like this, is in black paper, and the other one is in silvered paper, all from the same origami kind of packet, so all the same thickness, or at least as best as the manufacturer tried to do with those. So hopefully this will be a fair test. What I'm going to do is light this candle, turn it around and put it near-ish our two squares there, the black one and the silver one, and allow that heat to radiate from the actual candle. So when you have a candle or a match or pretty much any heat source in some planet that has an atmosphere like Earth, then what you're doing is that, like we looked at last lesson in the convection video, you're heating up the air particles above them. And so we get a lot of convection now above this candle. It's actually really quite warm above a candle. If you try and light a candle, put your hand above it, please don't leave it there for a long time, it hurts. You also get radiation heat coming from the side. You can sort of see my fingers lighting up there. That's because there's something called electromagnetic radiation, and it's the form of light, and it's landing on my fingers. But another form of electromagnetic radiation of just a slightly lower frequency or a longer wavelength is called infrared heat, and that radiates in the form of an electromagnetic wave in all directions, so up as well, but also to the sides. And so I can feel some heat coming off this candle here, and so that's radiation heat. So I want to see which kind of objects absorb this electromagnetic radiation infrared waves better. Matte black objects that are not shiny at all, or shiny silvered objects. If it really is behaving as an electromagnetic wave and its properties are similar to visible light, then there's less visible light reflecting off this black one than there is off this shiny silver one. So do you think we'll see temperature changes here? They're roughly the same temperature now. I won't start the experiment till they're at the same temperature, or within calibration anyway. What do you think? Okay, let's start the experiment. Which one will heat up the quickest? A, the black one. B, the shiny silver one. Or C, it will make no difference. Could be either of them. Let's see. The red temperature at the top there is the silver panel, and the blue one down there is this black one. Okay, so I'll actually do a time-lapse video just so we can keep this going for a long time, and you can keep track of those. I'll occasionally have to poke it so that the light comes on. Hopefully it won't run out of battery before the video stops. Okay, well, let's get started. So hopefully you could see from the video there that the darker black one is actually absorbing heat better than the shiny silver one. And so that is to do with what we just said at the start of this video. There is electromagnetic radiation. If you don't really know what that is, don't worry, it's just like light, basically. There's a wave being emitted from all glowing objects, all hot objects, and our eyes can only detect a certain frequency or a certain wavelength that's being emitted from this in the visible light spectrum, or the visible light region, from red to violet. But if we had a longer wavelength than red, our eyes wouldn't be able to see it. But all those tiny temperature receptors on our skin and on our hands and face and all over us, they can detect this infrared radiation. And so you may have noticed, if you ever go outside on a hot day, if you're wearing, on a really sunny day, if you're wearing black, you're probably going to feel quite warm. If you're wearing white, it's going to reflect the sun's heat away and you won't get so warm. So have a little think about any examples where a certain material or colour is used or in some kind of design to either reduce the amount of heat that's absorbed by something or increase the amount of heat absorbed by something. Maybe human-made or maybe somewhere in nature. But there are actually lots of examples. You could even test this yourself. You might not have these thermometers, but you do have temperature receptors in your skin. You've got fingers. I was playing around with these with my daughters before, and they were putting their fingers in each one and seeing which one they thought was heating up the most. They had to hold their fingers at the same distance, of course, to make sure it was a fair test. That would be their control variable, the distance from the heat source. But of course, if you are doing this, please take care. These are by no means heat proof. Okay, if you actually put them in the flame, they will set on fire. Also, this is only for heat radiation. Notice that even when I had the candle close, it wasn't touching the panels, it was just radiating some heat to them. That's important to note. There's no conduction taking place here, and any convection currents due to the air heating up are going to go up. Occasionally you'll see these whiffs of sort of black smoke, a bit of carbon, incomplete combustion, there we go, and they go straight up. That's just showing you that the heat is causing the hot air to rise in a convection current. It's the radiation that's moving against this wall as an electromagnetic wave, because that's an important point. Radiation, or heat transfer by radiation, does not need any particles like conduction and convection do. They both rely on particles. Heat radiation doesn't. And that's why we can get heat from our heat source to us without touching anything. Even if I took all the air particles away, I'd still feel the heat in the form of radiation. I wouldn't get any convection, so the temperature would just feel the same all around. Whereas now, because of the convection, it feels a lot hotter above the flame. And this is also the same reason why on Earth we can get heat from the sun, when between the Earth and the sun is nothing but space. And space is a vacuum, which means no particles, which means there can be no conduction, no convection, but there can always be radiation.